A quiet tension settled over observatories across the solar system. On a clear Martian night, when the pale red dust swirled gently in thin winds, a signal arrived from the outer solar periphery that would immediately ripple through the scientific community. 3I Atlas, an interstellar visitor already remarkable for traversing unfathomable distances across the void, had performed a maneuver that no natural body should have been capable of. Its path, once predictable by conventional orbital mechanics, suddenly veered in a manner that startled both veteran astronomers and computational models alike. The instruments picked up a subtle yet undeniable acceleration, imperceptible to the naked eye but unmistakable to the arrays of highly sensitive detectors tracking near Mars space. Within hours, alarms were sounded. Not the clanging warnings of panic, but the urgent, measured alerts of professionals who understood that the cosmos sometimes whispers in anomalies before roaring in catastrophe. Scientists at NASA, ESA, and observatories in Chile, Hawaii, and beyond immediately reoriented their telescopes and radar arrays. Every photon, every reflected wavelength of light was meticulously captured, forming the first threads of a story that was as yet impossible to narrate fully. Interstellar bodies are already rare, an event once every few years at most. But for one to interact with Mars in this extraordinary way bordered on the unthinkable. The cosmic choreography of planets, moons, and asteroids, governed by the immutable laws of gravitation and inertia, seemed momentarily suspended. 3I Atlas did not merely drift past. It exhibited intent, or at least behavior, that suggested an unknown force was guiding it. In the control rooms, models ran frantically. Calculations of potential trajectories, simulations of gravitational tugs from Mars and the Sun, even scenarios incorporating hypothetical propulsion mechanisms. Nothing aligned with expectation. Observers noted a peculiar silence surrounding the event. Unlike comets that reveal themselves through tails and outgassing, or asteroids traced easily by reflected sunlight, this object seemed aloof, almost self-contained. Its approach was not violent, but there was an unmistakable gravity to its presence, an implication that the universe still held secrets beyond human comprehension. The cosmic alarm was not merely about proximity, it was about possibility, a challenge to the boundaries of known physics, and a quiet invitation to rethink everything we understood about celestial mechanics. Even as data streamed in, a sense of awe mingled with trepidation. This was not a fleeting anomaly. It was a herald, a mysterious interstellar messenger performing an impossible ballet near the fourth planet, leaving humanity to watch, calculate, and wonder. The first glimmer of 3I Atlas came not as a headline or a broadcasted alarm, but as a series of faint, almost imperceptible blips on high-resolution telescopes stationed on Earth. Astronomers working under the clear skies of Mauna Kea in Hawaii noticed an object moving against the backdrop of distant stars in a trajectory unlike any known asteroid or comet. At first, it was assumed to be a standard near-Mars passing body. Yet, the subtle irregularity in its motion, a slight, inexplicable curvature, caught the attention of seasoned observers. It was as if the object were aware of its surroundings, nudging itself along paths that defied straightforward orbital predictions. The primary detection came through automated sky surveys like the Pan-STARRS telescopes, designed to continuously scan for moving objects. The initial flagging of 3I Atlas was based on its hyperspeed velocity and a preliminary calculation of its hyperbolic excess velocity, which immediately marked it as an object unbound to the Sun, a true interstellar visitor. However, a deeper analysis of the initial arc by astronomers, like Dr. Elena Vasquez, who specialized in high-velocity transients, quickly revealed the first red flag, a non-random, slight deviation from the predicted hyperbolic curve. The detection process was painstakingly slow at first. Arrays of sensors calibrated to detect objects just a few kilometers in diameter captured reflections of sunlight that bounced off what was later revealed to be an unusually reflective surface. Specialized software designed to filter standard near-Earth and near-Mars orbiting objects repeatedly flagged this body. It moved too fast, too erratically, and at angles that conventional Newtonian mechanics could not readily explain. Telescopes in Chile's Atacama Desert, including instruments from the European Southern Observatory, corroborated the observation, providing a second independent dataset that confirmed the initial detection. Astronomers refined their readings nightly, adjusting for atmospheric turbulence, parallax, light diffraction, and the subtle gravitational influences of Mars and its moons. The difficulty was in the object's subtlety. It was almost ghostly, a faint silhouette streaking across deep space. Yet every photon recorded told a story of extraordinary velocity, unusual composition, and an interstellar origin that no ordinary solar system body could claim. The object's brightness, trajectory, and near-Mars approach were precise enough to rule out mundane explanations like observational error, satellite interference, or computational glitches. In laboratories thousands of miles away, physicists gathered to cross-reference spectral data, comparing it against the known signatures of everything from common chondrites to Kuiper belt objects. No match was found. What they were witnessing was real, immediate, and fundamentally puzzling. The first detection was the opening note of a cosmic symphony, whose movements would challenge centuries of astronomical understanding. This was no ordinary asteroid. It was a herald from beyond, demanding scrutiny, reverence, and a readiness to confront the impossible. As 3I Atlas edged closer to Mars, it became evident that its journey through space was far from ordinary. Orbital models, initially confident in predicting its passage based on conventional celestial mechanics, began to falter catastrophically. Simulations showed persistent discrepancies, not random noise, but systematic deviations in velocity, unaccounted for curves in its path, and subtle accelerations that no gravitational calculations could explain. The residuals, the differences between the predicted position and the actual observed position, grew alarmingly large with each passing hour. Astrophysicists used sophisticated N-body simulations, which account for the gravitational influence of every major body in the solar system, from the Sun to Jupiter, and even the subtle tugs of the main asteroid belt. Yet, no matter how complex the simulation, the residuals for 3I Atlas stubbornly persisted. The object was defying the equations. It was as if the body were actively generating momentum or mass, negotiating the solar system with a precision that mocked centuries of Newtonian assumptions. The trajectory data revealed more than simple anomalies. It suggested something almost imperceptibly strategic. Standard objects, whether comets ejected from the Oort cloud or interstellar wanderers like Oumuamua, follow predictable arcs determined solely by gravitational forces and minor non-gravitational forces like the Yarkovsky effect, the subtle thrust from solar heating. 3I Atlas, however, subtly adjusted its path in ways that could not be explained by any of these known effects. The required magnitude and directionality of the non-gravitational acceleration exceeded the limits of the Yarkovsky effect by several orders of magnitude, and its profile did not match known cometary outgassing. Ground-based radar imaging added further layers to the puzzle. Each radar ping returned data showing a non-uniform movement pattern, slight lateral drifts, irregular spin rates, and minute changes in the approach angle toward Mars. The most alarming component was the lateral shift, a change in position perpendicular to the direction of motion. This component required a sustained, directed force, fundamentally at odds with the passive drifting expected of an inert space rock. These deviations, while minute, accumulated over millions of kilometers, producing a trajectory that deviated from initial projections by thousands of kilometers. For orbital mechanics, such discrepancies are monumental, prompting urgent recalculations and calls for additional observations. The scientific community began to grasp the philosophical weight of the phenomenon. Here was a body arriving from the interstellar void, not passively drifting, but displaying behaviors that flirted with agency, or at least a level of physical complexity beyond known natural processes. The trajectory alone raised questions. Could there be forces at play beyond standard gravitational theory? Might dark energy, unseen interactions, or even exotic matter influence its path? The object's movement forced a profound reconsideration of the assumptions underpinning celestial dynamics. 3I Atlas was not merely passing by. It was redefining the parameters of what could exist within our solar neighborhood. As 3I Atlas drew closer, astronomers and planetary scientists turned their attention to its physical characteristics, seeking clues hidden in the light it reflected. Early measurements obtained through spectroscopy and photometry hinted at an unusual composition that distinguished it starkly from conventional asteroids or comets. Its surface reflected light in a manner inconsistent with rocky or icy bodies commonly observed in the solar system. The spectral lines were the first major clue. They indicated high concentrations of refractory metals, specifically high-purity nickel and iron alloys, but interspersed with elements far rarer in such ratios, such as iridium, platinum group metals, PGMs, and even traces of anomalous isotopes. The presence of these PGMs, normally only found dispersed in trace quantities, suggested a formation environment radically different from our own solar nebula, perhaps originating in a distant, metal-rich star system with unique stellar processes or extreme thermal differentiation. Infrared sensors revealed further anomalies. While standard interstellar objects often exhibit volatile outgassing, forming faint tails detectable in multiple wavelengths, 3I Atlas remained remarkably inert. Spectroscopic analysis confirmed a notable absence of characteristic absorption bands for water ice, carbon monoxide, or silicates, the building blocks of most solar system bodies. It appeared to be made of highly compacted, non-volatile material. Despite its close proximity to the Sun and the warming effects of the inner solar system, its surface appeared unusually solid and reflective, almost polished, as if buffeted and shaped by forces unknown during its long voyage through the galactic void. The thermal inertia, its resistance to changing temperature, was unusually high, implying an internal structure designed for durability. High-resolution imaging revealed regions of unexpected smoothness and high reflectivity. Certain facets gleamed in sunlight, suggesting the presence of metallic compounds or highly compacted minerals. Crucially, the light curve analysis showed that the reflectivity did not match a uniform distribution. Instead, the distribution of these reflective patches appeared almost deliberate, too uniform and coherent to be purely natural. High-resolution imaging revealed certain protrusions on the object's surface exhibited angular geometries, sharp edges, straight lines, and right angles that hinted at non-random formation processes, producing shadow patterns inconsistent with erosion or collision-based sculpting. This finding was the most controversial, pushing the discussion from unknown physics toward the realm of the truly inexplicable. Radar measurements offered additional perplexing details. The object's size, estimated from reflected radio waves, was larger than initially assumed, with an elongated, irregular shape that defied simple geometric models. Spin rates inferred from subtle changes in radar reflections over time suggested a rotation too rapid for a body of its size to maintain structural integrity under conventional physics. Material strength theories would normally predict catastrophic fragmentation under such rotational stress. Yet 3I Atlas remained coherent, seemingly resistant to the stresses of rapid rotation and solar radiation. Its mere presence, combined with these extraordinary measurements, compelled scientists to question assumptions and consider possibilities that once belonged solely to theoretical speculation. Within hours of confirming the irregular behavior of 3I Atlas, NASA issued its first formal alert, a carefully worded notice to observatories, research institutions, and space agencies worldwide. It was not a declaration of imminent danger, but a recognition that this object defied existing predictions and required immediate coordinated observation. The alert emphasized the object's approach near Mars, its unusual acceleration, and its spectral anomalies, instructing teams to prioritize its tracking across multiple wavelengths and instrumentation platforms. Control rooms at NASA's Jet Propulsion Laboratory and Goddard Space Flight Center shifted into heightened operational states. Satellites and telescopes were retasked, computer models were recalibrated, and observation schedules were rewritten. Every orbital asset capable of detecting the object, from the Hubble Space Telescope and the Chandra X-ray Observatory to the newly deployed James Webb Space Telescope, JWST, and the Mars Reconnaissance Orbiter, MRO, was considered for potential contribution. The JWST was tasked with gathering detailed infrared spectroscopy to probe for the faintest signs of volatile compounds or complex organic molecules. The alert triggered an immediate response from international partners. The European Space Agency, ESA, retasked deep space tracking stations, and JAXA, Japan Aerospace Exploration Agency, and CNSA, China National Space Administration observatories, began coordinating with NASA, sharing data streams and observational protocols. The object, invisible to casual skywatchers, had become the focal point of a global network of eyes trained on the heavens. This full-scale international collaboration was reminiscent of the efforts to study Oumuamua, but the tone was significantly more urgent due to the object's proximity to a planet, vital for ongoing robotic missions. Streams of data began pouring in from an array of instruments: optical telescopes, infrared arrays, radar facilities, and space-based observatories. The sheer volume of information was staggering. Within hours, petabytes of raw measurements flooded secure servers, challenging data processing pipelines. Scientists worked feverishly, in shifts to distill meaningful patterns from this torrent. The object's rapid acceleration and unorthodox trajectory required multiple triangulations. Ground-based arrays measured parallax and Doppler shifts, while space telescopes provided high-resolution imaging unaffected by atmospheric distortions. Integrating these diverse data streams demanded not only raw computational power, running massive supercomputer clusters, but deep expertise in astrophysics, orbital mechanics, material science, and even esoteric branches of physics. Teams collaborated virtually across continents in secure, dedicated channels, often working around the clock to ensure that the anomaly was captured in every measurable detail. Despite the deluge, patterns began to emerge. Variations in brightness hinted at an irregular, perhaps metallic surface, while unexpected fluctuations in trajectory suggested forces acting in ways beyond simple gravitation. The collaboration itself, A convergence of minds, machines, and global coordination mirrored the vastness of space. As observational focus intensified, attention shifted to the impossible rotation of 3I Atlas. Precise photometric analysis revealed a spin rate that profoundly confounded expectations. Measurements showed the object spinning at a rate unusually rapid for its estimated size and composition, completing a rotation in just a few hours. Furthermore, its axis of rotation was not stable, but displayed a complex precession, suggesting more than simple tumbling. The rate of spin was the most critical physical anomaly. Conventional calculations predicted that a body of 3I Atlas's estimated size, composed largely of metallic and refractory material, would have an insufficient tensile strength to remain intact under such rotational stress. At this angular velocity, the centrifugal force at the equator should have easily overcome the material's cohesive gravitational and internal mechanical strength, leading to fragmentation. Yet, the object remained stubbornly coherent. This structural resilience implied several highly speculative possibilities. One hypothesis was that the object was composed of an alloy with a tensile strength far exceeding anything known in terrestrial or solar system materials, perhaps due to formation under extreme, high-pressure conditions in a distant stellar system. Another, more radical idea suggested that the object possessed an active internal structure, a network of dense, interlocked components, or even a dynamically maintained internal balance that counteracted the centrifugal forces. The precessing spin, combined with the irregular shape, introduced further complications for trajectory modeling. The changing orientation relative to the Sun meant that any non-gravitational effects, such as solar radiation pressure acting on the reflective patches, would be constantly modulated. Scientists had to continuously recalibrate models to account for the object's angular momentum interactions with Mars's local gravitational field. The rotation was not a secondary effect. It was a dynamic parameter inseparable from trajectory, composition, and thermal behavior, complicating every predictive model. The light curve, the graph of brightness over time, was equally complex. It showed not a smooth, sinusoidal variation expected from a uniformly reflective, elongated object, but sharp, intermittent gleams that correlated with the angular geometries observed in high-resolution imagery. These gleams suggested highly polished metallic facets that acted like mirrors, briefly catching the Sun's light at specific rotational phases. The impossible spin and the highly structured surface texture collectively pointed toward an object that was not merely a passive wanderer, but a body of exceptional, almost engineered, durability and complexity. As 3I Atlas drew nearer to Mars, the subtle interplay of gravitational forces became increasingly pronounced, revealing anomalies that confounded scientists. Mars orbiting satellites detected minuscule perturbations, slight shifts in orbiting trajectories, and unanticipated variations in local gravitational fields. While these deviations were small in absolute magnitude, they were significant enough to suggest that the interstellar visitor was exerting forces inconsistent with its estimated mass based on size and typical asteroid density. Traditional gravitational calculations failed to account for the localized influence. This left researchers to speculate about hidden mechanisms. Could the object possess a core of anomalously dense material, perhaps super-heavy elements, or an internal configuration that effectively amplified its gravitational tug? The idea of a non-uniform, dense internal structure gained traction, but even the most optimistic density estimates failed to fully reconcile the observed gravitational effects. Furthermore, simulations of Mars's gravitational field, integrating real-time data from multiple satellites, indicated minor but detectable distortions coinciding with 3I Atlas's passage. These distortions did not match expectations based on a purely Newtonian gravitational model. The possibility of lens-thirring precession, or frame dragging, a subtle effect of general relativity, where a massive spinning object distorts the space-time around it, was incorporated into models. While frame dragging is negligible for solar system objects, the anomalous density and rapid, complex rotation of 3I Atlas required this relativistic consideration. Still, even this advanced physics could not account for all the residuals. Amid the mounting anomalies, 3I Atlas revealed a crucial layer of complexity: unexpected magnetic properties. Sensitive magnetometers aboard Mars-orbiting satellites, including the MAVEN mission designed to study the Martian atmosphere, registered minute but persistent fluctuations coinciding with the object's passage. These signals were subtle, yet consistent across multiple instruments, indicating that 3I Atlas possessed organized, localized magnetic fields, unlike those typically observed in inert interstellar debris. The magnetic anomalies posed immediate questions about composition and internal structure. The strength and orientation detected suggested an organized, heterogeneous magnetic distribution within the object. Natural metallic asteroids generate faint, randomly oriented remnant fields from their formation history. In contrast, the fields detected on 3I Atlas appeared non-uniform and dynamically interacting with the surrounding solar wind and Mars's own magnetosphere. The organization of the field hinted at structured flow of current or a unique, highly aligned crystalline structure within the metallic alloys. This dynamic magnetic interaction reinforced the notion that 3I Atlas was not passive but actively engaged through its physical properties with the environment around it, potentially contributing to its peculiar trajectory or resistance to predicted orbital forces. Some theorists even proposed a mechanism where the interaction between the object's magnetic field and the highly conductive solar plasma could produce a minute magnetohydrodynamic (MHD) thrust, though the energy requirements remained astronomical. As 3I Atlas executed its impossible ballet near Mars, the global scientific community was simultaneously engaged in a crucial risk assessment. While the object posed no immediate threat to Earth, its unpredictable nature near Mars, a planet populated by active and valuable robotic assets, warranted immediate concern and contingency planning. The most pressing risk was the potential for collision with Mars-orbiting satellites. Missions like the Mars Reconnaissance Orbiter, MRO, Mars Odyssey, and the European ExoMars Trace Gas Orbiter operate in carefully defined, high-value orbits. Even minor inaccuracies in 3I Atlas's trajectory prediction could have cascading effects, requiring emergency collision avoidance maneuvers. Orbital dynamicists worked around the clock, using the best-fit models, despite their persistent failure to fully explain the object's motion, to calculate the probability of a close approach within the sphere of influence of any satellite. Risk assessment required integrating all the anomalous data. Rotational dynamics, which could shed debris, surface anomalies, and magnetic interactions were modeled alongside gravitational influences. Simulations considered extreme but plausible scenarios. Would the object's impossible spin cause it to shed fragments that could pepper the Martian atmosphere or hit a satellite? Would the powerful, localized magnetic field interfere with sensitive satellite instrumentation? And most profoundly, what was the impact probability for a direct hit on Mars itself? And what would the consequences be given the object's high-density, metal-rich composition? While none of these catastrophic outcomes appeared imminent, the exercise underscored the necessity of proactive monitoring and scenario planning. The broader, more theoretical cosmic risk was also evaluated. 3I Atlas's anomalous acceleration demonstrated that even a small interstellar body could behave in ways that fundamentally challenge predictive models. This raised critical, long-term questions for planetary defense. If the laws of orbital mechanics can be defied by interstellar visitors, then existing protocols, which rely heavily on precise predictability, may need a complete overhaul to account for unknown non-gravitational forces. The object's passage became a wake-up call, emphasizing that the universe's unpredictable intricacies must be fully integrated into models of cosmic security. The scientific community soon realized that 3I Atlas's behavior was sending metaphorical shockwaves through the frameworks of astrophysics and planetary science. Newtonian mechanics, while immensely successful for centuries, now appeared insufficient to account for the object's complex dynamics. Even Einstein's relativistic corrections could explain only a fraction of the anomalies. The persistent failure of conventional models prompted a vigorous debate and the formulation of leading hypotheses. Exotic natural mechanisms. Some researchers suggested that interactions with dark matter could produce subtle, non-gravitational forces influencing its acceleration and trajectory, especially as it passed through regions of higher dark matter density near Mars. In this speculative scenario, 3I Atlas could possess a unique cross-section or composition that interacted selectively with the local dark matter halo around the Sun, resulting in a measurable, directed force. Other natural hypotheses explored the role of internal heterogeneity, layers of metallic and refractory compounds within 3I Atlas could have responded differentially to solar radiation, creating asymmetrical forces capable of producing minor accelerations. Computational models incorporating these effects could reproduce segments of its behavior, though they failed to entirely account for the lateral deviations or the precise rotational precession observed. Frontier physics. In attempting to explain the anomalies, scientists turned to Einstein's theories of relativity, seeking insight into whether space-time curvature or gravitational time dilation could account for its unexpected motion. Relativistic modeling focused on how the curvature of space-time around Mars and the Sun might interact with a highly compact, dense object. Calculations included the minute effects of gravitomagnetism, the lesser-known effect where the motion of mass generates a component of the gravitational field, analogous to a magnetic field generated by a moving electric charge. While this provided a more comprehensive model, it highlighted the limits of even the most advanced, tested physics when confronted with this specific interstellar anomaly. Quantum and speculative concepts. As conventional and relativistic frameworks struggled, some theorists ventured into the domain of quantum mechanics and speculative physics. Concepts such as quantum tunneling, vacuum fluctuations, or interactions with zero-point energy fields became part of serious modeling discussions. One hypothesis proposed that 3I Atlas might interact with the quantum vacuum in a manner producing minute but persistent forces subtly influencing its trajectory, an extension of the Casimir effect to macroscopic scales. Highly speculative ideas such as localized quantum coherence within the object, perhaps due to exotic alloys, were also explored as potential mechanisms for its rotational stability and resistance to centrifugal stress. These discussions, though speculative, emphasized that the universe might operate with layers of subtlety beyond human observation. Artificial or engineered mechanisms. While controversial, artificial or engineered mechanisms could not be entirely dismissed, particularly given the angular geometries and the persistent, directed, non-gravitational acceleration. The possibility was framed not as an assertion of intelligence, but as a necessary framework to explore when all known natural explanations failed. Theorists considered whether the object could be a derelict piece of extraterrestrial technology, perhaps a type of interstellar probe. The reflective metallic facets, for instance, could be part of a non-functional light sail whose partial damage or asymmetric structure led to the observed erratic acceleration. Alternatively, the magnetic anomalies could hint at a passive or active magnetic field generator designed for interstellar navigation or shielding, whose decay led to the erratic magnetic influence observed. Models of directed propulsion, magnetic field interactions, or even controlled mass redistribution were tested in simulations, demonstrating partial consistency with observed behavior. In all cases, leading hypotheses emphasized the extraordinary nature of 3I Atlas. No single explanation was wholly sufficient. Each accounted for fragments of observed behavior while leaving others unresolved. This multiplicity reflected the object's complexity and the novelty of its interstellar journey. 3I Atlas, through these hypotheses, challenged scientists to think creatively, rigorously, and expansively, reminding the community that the universe could behave in ways that were subtle, profound, and entirely unexpected. Amid the torrent of observational data, scientists began to detect subtle patterns in 3I Atlas's behavior. Its trajectory, though irregular at first glance, exhibited recurring deviations at predictable rotational phases, suggesting an underlying order amid apparent chaos. Each spin revealed consistent alignments between reflective metallic regions and lateral acceleration vectors, hinting that structural or compositional asymmetries influenced motion. These emergent patterns provided the first coherent hints that the object's anomalies were not random, but instead followed physical principles that were previously unconsidered in celestial mechanics. Spectroscopic observations added further layers to the emerging patterns. Specific elemental concentrations corresponded with reflective anomalies, indicating that metallic-rich regions might be influencing the object's interaction with solar radiation or the interplanetary magnetic field. Thermal imaging showed that these same regions absorbed and re-radiated energy differently than adjacent surfaces, subtly affecting rotational dynamics. The pattern suggested a differential response to solar heating, a phenomenon where one side of the object gained more energy than the other, creating a predictable, subtle thermal thrust that repeated with the rotation cycle. The combination of chemical, structural, and rotational patterns painted a picture of an object exhibiting complex interdependent behaviors across multiple physical domains. Even magnetic measurements suggested recurring patterns. Fluctuations in local magnetic fields correlated with rotational phase and surface composition, indicating that magnetic interactions could be contributing to the object's trajectory and acceleration. This interplay between rotation, composition, and magnetism hinted at a coherent system of forces acting upon 3I Atlas, reinforcing the idea that the anomalies were intrinsic rather than artifacts of measurement or environmental perturbations. The emergence of these patterns allowed scientists to refine models, narrowing uncertainties in trajectory predictions and improving understanding of rotational behavior. The universe, even in its most mysterious manifestations, often conceals a hidden structure, waiting for observation and analysis to uncover its logic. This was the core lesson. The impossible was simply a pattern of behavior whose underlying mechanism was yet to be understood. The unfolding story of 3I Atlas generated a profound sense of cosmic awe, reverberating beyond the scientific community into the consciousness of humanity itself. Observers, technicians, and theorists alike were confronted with the majesty of an interstellar traveler that had journeyed unimaginable distances, surviving the cold void of space, and now performing behaviors that defied prediction. Each observation, every reflective glint, rotational shift, and trajectory anomaly served as a reminder that the universe is vast, complex, and capable of exceeding the bounds of human expectation. This awe was intellectual, born of the interplay between observed phenomena and the limits of understanding. The incomplete understanding fostered a deep appreciation for the intricacies of interstellar physics, the delicate balance of forces governing matter, and the subtle interactions that could alter trajectories across light years. The cosmic scale of the phenomenon amplified its emotional resonance. 3. Atlas's journey had begun long before humans existed, traversing the galaxy with indifference to terrestrial concerns. Its passage near Mars was fleeting yet historically significant, a reminder that humanity's window to observe such events is narrow and precious. Even as 3I Atlas receded into the depths of space, its influence on the Martian vicinity gradually diminished, leaving behind a trail of scientific intrigue and human contemplation. Its departure was neither violent nor abrupt. It slipped silently along its path, moving away from Mars with the same subtle, precise maneuvers that had defined its approach. Its rotation, magnetic field fluctuations, and reflective metallic patches continued to evolve in ways only partially recorded, leaving scientists with partial data sets that would fuel years of research. The object's passage became a permanent reminder that the universe contains phenomena at once beautiful, elusive, and inexplicably complex, demanding both careful measurement and philosophical reflection. The lingering questions were not failures of understanding, but invitations to continue exploring, testing, and marveling at the cosmos. As the light from 3I Atlas faded into the infinite darkness of space, a quiet stillness settled over the instruments and minds that had followed it so intently. The rush of data, the hum of calculations, the tense anticipation, all gave way to quiet reflection. The universe, immense and indifferent, had whispered a story, and we had listened. The interstellar visitor may have departed, yet its story lingers, echoing softly through our minds, urging patience, humility, and the ceaseless pursuit of understanding. The universe, immense and indifferent, had whispered a story, and we had listened. The interstellar visitor may have departed, yet its story lingers, echoing softly through our minds, urging patience, humility, and the ceaseless pursuit of understanding. If you found this cosmic mystery as compelling as the scientists who tracked it, you need to be part of the community that explores the frontiers of space and physics. Subscribe to Stellify Science right now. Hit that notification bell so you don't miss our next deep dive into the universe's most mind-bending enigmas. We're decoding the impossible, one anomaly at a time. Join us as we continue to watch, measure, and ponder the cosmos. The endless frontier is waiting. Subscribe today to Stellify Science and never stop looking up.